All right, let's jump right in. We've all heard it 1,000 times, right? It's like the first rule of the universe. Nothing can travel faster than the speed of light. It's supposed to be this absolute, unbreakable law. But what if I told you there's a catch? Because get this, that question on your screen isn't just a hypothetical. It's based on a real measurement from a particle accelerator. Scientists took an electron and got it going so fast that, by one way of looking at it, its velocity was a mind-boggling 88,000 times the speed of light. So, what gives? Do we just break physics? Well, the answer is kind of weird. It's no, but also in a really cool way, yes.
Okay, to unravel this whole thing, we've got to talk about the universe's speed limit. The problem is our normal, everyday intuition about how speed works, car plus another car's speed, it just totally falls apart when you get to cosmic scales. And that brings us to the big one, c, the speed of light. It's not just some random fast number, It's woven into the very fabric of space-time. Think of it like a hard wall, an absolute cosmic speed limit. If you have mass, and everything we know does, you can get really, really close to it, but you can never, ever hit it, let alone break through it. So let's be clear, this speed limit is very, very real. So here's where our brains get twisted into a knot. Our intuition, right, tells us that if you're on a spaceship moving at 80% the speed of light, and you shoot something forward that also goes 80% light speed, you just add them up. 0.8 plus 0.8 equals 1.6. Easy, we've broken the light barrier. But the universe has other plans. The reality of relativity is just weird. When you do the actual math, that combined speed is still less than the speed of light. Our simple addition just doesn't work in this neighborhood. So if the speed limit is unbreakable, how in the world do we get to a number like 88,000 times the speed of light? Well, we don't break the rule. We just find a new way to measure speed. It's all about changing your perspective. Instead of watching from the sidelines, we're going to measure things from the traveler's point of view. First up, let's talk about the speed we all get. Ordinary velocity. We'll call it v. This is exactly what the speedometer in your car measures. It's super straightforward. It's the distance someone on the sidewalk sees you travel, divided by the time on their watch. Easy peasy. But now, here's the magic trick. This is proper velocity, which we'll call w. We keep the distance the same, the distance a stationary observer measures. But, and this is the whole shebang right here, we change the clock. We divide that distance by the time experienced by the traveler. And here's the kicker from Einstein. The faster you move through space, the slower time moves for you. So we've got these two different speedometers, right? One for the observer and one for the traveler. Let's see what happens when we compare them, because they tell two very different stories. Okay, so look at this. For something slow, like a car, your clock, and the clock of someone on the sidewalk are ticking at pretty much the same rate. So ordinary velocity and proper velocity, they're basically the same number. But look what happens when you get a particle moving near the speed of light. Its personal clock slows down, way down. It almost stops. And when you divide a big distance by a teeny tiny amount of time, the result is a huge, enormous number. And boom, there it is. This is the answer to that puzzle we started with. That electron at CERN, its ordinary velocity, v, was stuck at 0.999% the speed of light. The needle was penned right against the cosmic speed limit. But its proper velocity, w, because its own internal clock had slowed to a crawl, from its perspective, it was blazing across that distance at 88,000 times the speed of light. See, it didn't break the law. It was just using a different and much cooler speedometer. Okay, so you might be thinking, all right, that's a clever math trick, but is it real? And the answer is absolutely yes. This isn't just a party trick for physicists. Proper velocity actually points to something much deeper about how motion works, and it even makes some of the physics more elegant. And here's a huge reason why. Remember from high school physics? Momentum equals mass times velocity. Simple, elegant. But that beautiful little equation completely falls apart when you get close to the speed of light. But guess what? If you swap out ordinary velocity v for proper velocity w, the equation works again. P equals m times w. It works perfectly at any speed, from a crawl to near light speed. That's a giant clue that proper velocity isn't just a quirky alternative. It's arguably the more fundamental way to measure motion. So when you boil it all down, That's what this is all about. Proper velocity is simply how fast you're covering ground according to your own clock. It's your personal speedometer. And because your personal clock can slow down infinitely as you approach the speed of light, your personal speed has no upper limit at all. And this is where things go from theoretical physics to straight-up science fiction territory. Because this idea of a personal, limitless speedometer has some absolutely mind-bending consequences for interstellar travel. So let's picture this. Imagine we have a spaceship that can accelerate constantly at 1g. That's the same pull of gravity you feel standing on Earth right now, so you'd feel totally comfortable inside. The plan is simple. You accelerate for the first half of the trip, then you flip the ship around and decelerate for the second half so you can actually, stop when you get there. All right, now hold on to your hat. If we wanted to take that ship to the Andromeda Galaxy, our closest galactic neighbor, the clocks back on Earth would tick forward more than 5 million years, a ridiculously long time. But for the crew on that ship, because their own personal time slows down so incredibly much as they approach light speed, the entire journey would take them only about 57 years. Think about that. You could travel to another galaxy in your lifetime. So let's just quickly pull all this together. Your ordinary speed, v, is always stuck below the speed of light. That's the law. But your proper speed, w, which is distance measured against your time, has no limit whatsoever. As your time slows, your proper velocity can just keep climbing. And that's the theoretical key to crossing these unimaginable cosmic distances in a human lifetime. And I want to leave you with this final kind of weird thought. We've just established that time isn't this universal absolute thing. It's personal. It depends on how you're moving. So if time is relative, what does that say about distance? Is that immense gulf between the stars really as fixed as it seems? Or is space itself also personal?